Juno launched 5 years ago, and it completed its journey to Jupiter this summer on Independence Day. It was a Jupiter orbital insertion. It was really exciting, and it was successful. So right now it's in the process of completing 2 staging orbits, which are very large, and then it'll tighten its orbit into these 2 weak science orbits, and it's going to be streaming data back. So the data I'm interested in is it's going to measure Jupiter's normalized moment of inertia to an accuracy of about 0.2%. And this is the moment of inertia divided by the mass of Jupiter times its radius squared. And this is of interest because it tells us about the distribution of mass within the planet. So specifically, okay, well, here's a picture of the launch from Cape Canaveral. Specifically, we are interested in learning about the core, which, well, what is the core? It's defined as the central concentration of elements that are heavier than hydrogen and helium, and we don't really know much at all about it. So specifically, I want to learn about how big it is, so its size, and how massive it is. We know precisely, what we do know is the total radius and mass of the whole planet. So if we combine that knowledge with Juno's measurement of alpha, then we can narrow the range of possible values that the core can take on for its radius and mass. And why do we want to do this in the first place? Well, we want to have a better understanding of Jupiter's structure as a whole, because that teaches us about how Jupiter formed in the first place, which has to do with the creation of our solar system. So, in summary, my analysis quantifies the extent to which uncertainties in the equation of state affect the determination of Jupiter's core. Here is an artist's concept of what the inside of Jupiter might look like. Okay, so, well, what's an equation of state? It's essentially a mathematical relationship that describes how substances, atoms interact with each other. It expresses the state of matter that arises from a given set of physical circumstances. Jupiter is mostly made up of hydrogen. So hydrogen has a very complex equation of state, but it's similar to a much more simple equation of state called the n=1 polytrope, which is right here. It's pressure equals K times rho squared. So P is pressure, rho is density, and K is a constant. And this only applies, in my model, only applies to Jupiter's envelope, which is the region external to the core. And I say that because I'm treating the core like this uniform solid body that's very distinct from the envelope. So using that polytrope, using the polytrope, we can actually solve for the density. And once we have the density, we can solve for the core mass, the envelope mass, and alpha. And all of these equations only depend on our choice of the core radius and K in the polytrope. It's accompanied by a drop in the core mass that is more significant than before. It's about 10 to 20%. And this is interesting because it's a greater change than before, but remember that the core mass is only a few percent of the total mass of the planet. So this isn't, once again, this isn't going to have too massive an effect on alpha. So just to wrap up, what did we accomplish? Well, I succeeded in creating a perturbation of choice to the equation of state. So now somebody else can say, well, this is what I think the equation of state is, and they can give me a correction term, and then I can see how that affects the core mass, which was the goal. So we succeeded in doing that. However, this is a toy model. It can be definitely improved for greater accuracy. One such way to do that would be to treat Jupiter as a non-uniform rotating body, which we didn't do. We just kind of pretended that it was this isolated system and that the core was this solid thing inside it. But we know that even once we have the equation of state, the core can take on a range of possible radii and masses. So what we really need to do is examine more. We need to figure out better Jupiter's equation of state, and that would come from examination of the heavy element makeup of its core, envelope, and that kind of thing. So yeah.